This is the third and last video in the module on referenced properties and experiment controls. In the first video of the module, we talked about why we need referenced properties and why this is an important feature of Simio in order to perform direct comparison of multiple scenarios or system configurations without complicating experimentation. And in the second video in the module, we learned how to define reference properties for our server capacities. We performed some analysis and we looked at the side-by-side smart plots that are generated for different scenarios in our experiment. In this video, we're going to pick up from where we left off in the second video of the module. However, due to time limitations, I'm not going to go over the model again. So if you would like to learn more about the model development, its verification, and the reference properties that we've already added to the model, I would like to refer you to the related videos. The description of the system is same as before, so we have an arrival rate of 32 customers per hour, and you can see the service times here. 70% of the customers get their sandwich toasted, and 30% get cold sandwiches. Under the current policy, we need to maintain FIFO throughout the system. In other words, customers that want cold sandwiches cannot pass those that are waiting in the oven station to have their sandwich toasted. And also we have bulking, and whenever customers arrive, they'll look at the number in the system, and if there are more than 6 people in the system, they will bulk. So we're interested in evaluating the performance of the system during lunch rush, and specifically we would like to answer the following 2 questions. First, we would like to add 2 additional resources to reduce lost sales, and the question is where to put these 2 additional resources. So keep in mind that the resource can be either an oven or a new drink machine or a worker at any of these stages. The other question is what is the best operating policy under the new system configuration? Should we allow passing or just stick with the current no passing policy? The performance measures will remain the same. So we're going to use server utilization's average time in system for all customers, expected number in system, percentage of customers that bulk in average time in system per customer type, in other words, cold and hot sandwiches. But we will primarily use the percentage of customers that bulk to compare different scenarios or system configurations. What we basically need to do is evaluate different system configurations under the 2 policies that we have. In fact, if we would like to find the optimal system configuration and policy, we need to evaluate all possible scenarios. So when you think about this particular problem, we would like to pick 2 out of 5 stages for capacity expansion purposes. So basically we have a selection of 2 out of 5 options, which gives us 10 scenarios. And since we have 2 operating policies, we have a total of 20 scenarios that we need to evaluate using simulation. So in the second video in the module, we used reference properties to evaluate and perform a direct comparison of all of the possible capacity allocations under the current policy, which is the no passing policy. In this video, we're going to learn how we can use reference properties to perform a side-by-side comparison of all possible parameter configurations under both policies. Moreover, we're going to perform more analysis with different bulking thresholds and see how the performance of the system changes. Now let's go back to our model and see how we can use reference properties to compare the current policy that maintains FIFO throughout the system with an alternative policy that allows cold customers to pass those customers that are waiting at the oven. So we have done this before. So basically what we need is a connector that goes from the output node of the bread station to the input node of the veggie station, and we only want the cold customers to go through this link. Since we are distinguishing the type of the model entities using the processing time state value that we have defined for model entity, we can basically use link weights on our connectors to on these two connectors right here to route the right entity types in the right direction. So we know that the proc time on oven value for hot customers will be a value that is non-zero, triangularly distributed with these parameters. However, the value of the same state variable for cold customers will be 0. So what I can do, I can simply go back to my model and use the selection weight here to tell Simya that I only want those customers that I have a 0 processing time on the oven to take this route. So what I need to type for my expression is model entity, and then my state variable, proc time on oven. And if this is equal to 0, I want my entities, cold entities basically, to skip the oven and go directly to the veggie station. So that's my expression for the selection weight on my new connector. And for my other connector, the alternative condition would be model entity proc time on oven not equal to 0. So I have my conditions for my connectors set up. Now I can go ahead and run my model in step mode and check that all my cold entities will skip the oven and only hot entities will go to the oven. So I keep running my model in this step mode to make sure that this is exactly what is happening in my model, and make sure that my the logic that I just added to the model is working correctly. Of course, now I can create a new experiment and perform the same analysis we did for the current policy for my alternative policy that I just implemented. But now let's take a look at how we can set reference properties for my link weights so that I can still use a single experiment to perform all my analysis. So what I basically need to do here is set reference properties for the selection weight on my two connectors. So I'm going to select a set a reference property for my first connector, and I'm going to call it hot selection weight. And the second one, I'm going to again set reference property, and this one cold selection weight. And now if I go to my model definitions and properties, you will see that I have the two expressions in my reference properties that I just defined. So now I can go to my same experiment that I had before, and now I see the two new expressions or reference properties that appear as controls in my experiment. So now I can experiment with both policies all in one experiment. In order to do that, I'm going to copy my controls for the set of experiments that I performed and paste them here. So now I have all parameter configurations set up for the alternative policy that we just implemented. Now, in order to clarify that the first 10 scenarios relate to the current policy, I'm just going to change the selection weight for my first 10 scenarios for the hot selection weight to 1, and for the cold selection weight to 0, since nobody skips the oven in the current policy. So I ran the experiment for my scenarios under the alternative policy, and now if we go to our response results, we can see the s'more plots for all of our 20 scenarios here, and clearly we can see that the scenario where we allocate the capacities to the bread and veggie station perform best under both policies. So that will be scenario 2, which is under the current policy, and scenario 12 under the alternative policy. So now what I would like to do here is only focus on these two scenarios. So I'm just going to deselect all of my scenarios and just reselect scenarios 2 and 12. So now when I go to my s'more plots, I can see the two scenarios, and I can compare the two scenarios side by side. And as you can see, it seems that our bulking percentage is slightly better under the alternative policy when we allow passing for cold customers. And in fact, we can see a clear difference between the two policies under this capacity allocation if we compare the timing system for cold customers. So I just selected cold timing system, and as you can see, as we expect, since our cold customers do not wait for the hot customers in the oven, we expect to see a much smaller timing system for cold customers under the alternative policy. So far, we have learned how to create reference properties by making a right click on the property name and go to set reference property and create a new reference property. Now suppose we would like to evaluate the performance of the system under different bulking conditions. So for example, in my add-on process, at the output node of my source, I have set the bulking condition to the case where my number in system is greater than 6. Now suppose we're not sure about the exact threshold value, and we would like to experiment with different values here. Now in this case, the process to create a reference property is for this threshold value is slightly different. Now in this case, we need to manually create a property. So I'm just going to my model definitions and properties, and this time I'm going to create an integer property, and I'm going to call it bulking threshold. And I'm going to set the default value to 6, which was indicated in the original problem statement, and I'll make sure that the visibility is set to true, which is a default. So now when I go to my experiment, again, this new property appears as a control, and this time I would like to go back to the model and to my process, and now instead of directly putting the value for my threshold, I will just use the property that I just created. So I will just use a reference to that reference property. So here I just need to type bulking threshold, and it appears right here. So I'm going to say OK. So now my customer's bulk when the number in system is greater than this bulking threshold, which I specify in my reference property. So now what I would like to do is create a new experiment, and this time I'm just going to focus on the best capacity allocation, so 2 units of capacity at bread and 2 units of capacity at veggies. So let me go ahead and create the second scenario. So I just want the first scenario to be under the current policy, so I'm going to change the selection weight, the hot selection weight to 1, the cold selection weight to 0. And I'm going to complete this experiment table for different values of bulking threshold and system configurations. So here is my complete experiment table. Note that I have rearranged the order of my controls. So I have bulking threshold in the first column, and I vary my bulking threshold from 4 to 9, and I go back and forth from the current policy to the alternative policy. And then I have my capacities, of course, for my servers. I have defined my response, my primary response, bulking percentage. I have also renamed my scenarios so that the first character represents the bulking threshold and the second character represents the operating policy. So C stands for current policy, A is the alternative policy. I have run each scenario for 25 replications. So I can go to my response results in side-by-side SMORE plots and now see how the performance of the two alternative policies changes under the selected capacity allocation as we increase our bulking threshold from 4 to 9.